In this problem, the objective is to determine whether string S is a subsequence of string T. A subsequence means that S can be derived from T by deleting some or none of its characters without changing the order of the remaining characters. This concept is crucial in various applications, such as text processing, DNA sequence analysis, and more. Understanding subsequences is fundamental because they preserve the relative order of characters, which is often a key requirement in many algorithms and real-world problems. To tackle this problem effectively, I employed a structured approach using the two-pointer technique with the isSubsequence function. Here's a detailed breakdown of how I approached and implemented this solution. I initialized two pointers, I and j, both starting at 0. These pointers were used to track the current positions within S and T, respectively. The strategy involved iterating through both strings using a while loop until either S was completely traversed or T was exhausted. During each iteration, I compared the characters pointed to by S of I and T of j. If S of I matched T of j, it indicated that S of I could be considered part of the subsequence found in T. Consequently, I moved the pointer I forward to check the next character in S. Regardless of whether there was a match or not, I always moved the pointer j forward to continue scanning through T. Let's consider an example to illustrate this process. Suppose S equals ABC and T equals AHBGDC. Here's how the algorithm would work. I equals 0, j equals 0, compare S of 0, A with T of 0, A. They match, so move I to 1. I equals 1, j equals 1. Compare S of 1, B with T of 1, H. No match, so move j to 2. I equals 1, j equals 2. Compare S of 1, B with T of 2, B. They match, so move I to 2. I equals 2, j equals 3. Compare S of 2, C with T of 3, G. No match, so move j to 4. I equals 2, j equals 4. Compare S of 2, C with T of 4, D. No match, so move j to 5. I equals 2, j equals 5. Compare S of 2, C with T of 5, C. They match, so move I to 3. At this point, I has reached the end of S, which means all characters of S have been found in T in the correct order. Thus, the function returns true. Upon completing the loop, I verified whether pointer I had reached the end of S, I equals S.size. If true, it confirmed that S is indeed a subsequence of T, and I returned true. Otherwise, I returned false, indicating that S could not be formed from T in the required order. This algorithm is efficient, with a time complexity of O(n plus m), where n is the length of S and m is the length of T. This efficiency is crucial for handling potentially large strings in practical scenarios. To summarize, my implementation effectively addresses the problem by systematically comparing characters and advancing pointers based on the rules of subsequences. This method not only solves the immediate task, but also showcases an efficient and straightforward approach to solving string-related problems using fundamental programming techniques. And now, let's run this solution to verify that everything works properly before submitting.